Has dark matter been found? China's reusable rocket reaches orbit but doesn't stick the landing. A possible explanation for the matter-antimatter asymmetry. And in Q&A Plus, Gaia helps pin down a supernova that hit the Earth 10 million years ago. All this and more in this week's Space Bites. We've known about the mystery of dark matter for nearly a century. It started with observations of galaxies, the Coma cluster, galaxy cluster that was sort of spinning too rapidly. It should have been tearing itself apart. So there was clearly some kind of hidden mass that was holding the thing together. Or we don't understand gravity at the larger scales. But to actually pin down the particle that is causing dark matter, if it is some kind of particle, has been tricky and has kept physicists busy for nearly a century. The primary candidate that people are looking at right now is some kind of particle that doesn't interact with regular matter or barely interacts with regular matter and doesn't interact with itself, but maybe barely interacts with itself. And so most of the time, it only influences regular matter through its gravity. But if you pack enough of this stuff close together, it may interact with itself. A good analogy is the neutrino, right? The neutrino is this particle. It's very ghost-like. It can pass through, on average, a light year of lead without interacting with any of the atoms in the lead, but occasionally it does, and that's how physicists can detect it. In a cubic kilometer of water ice down in Antarctica, with the ice cube facility, occasionally you're going to get neutrinos that actually interact with the ice particles. So this idea of dark matter, that if you get it close enough, it could interact with itself or maybe regular matter and annihilate. If it does, then it'll give off this signature of gamma radiation. And so astronomers have noticed that there's an excess of gamma radiation coming from the center of the Milky Way. And this has been a puzzle that has been around for about 20 years or so. And this gamma ray excess, something is causing matter and antimatter to collide and produce this gamma radiation. And there's been a lot of ideas for what this might be, that there could be an excess of pulsars which have magnetic fields in the area and they're interacting with their environments, producing antimatter. The antimatter is finding matter, and you're getting this excess of gamma radiation coming from the center of the Milky Way. But the other idea, the intriguing idea, is that there is enough concentration of dark matter near the center of the Milky Way, sort of shepherded by the supermassive black hole at the center of the Milky Way, that you're getting these dark matter annihilations. A new study has come out where a team of Japanese astronomers have mapped the gamma radiation that's coming from the center of the Milky Way. And they found that it fulfills a lot of the expectations, the predictions of what you would get from annihilating dark matter. So first, there's the shape, kind of the halo of where this radiation is coming from matches the simulations for where the dark matter should be concentrated. The quantity, the number of these interactions, the amount of particles that are being sent out, sort of matches that if you have particles that meet within this criteria, then you could get that amount of radiation coming, and that seems to match as well. And it matches the spectrum that you would expect from this annihilation. This is really intriguing. We've got this explanation, not only for this excess of gamma radiation coming from the center of the Milky Way, but also an explanation for what dark matter is, or at least it meets some of this criteria and seems to be annihilating at the center of the Milky Way. Now, this is one of those very big, interesting if true results, and so there's going to be a very big skeptical response from the astronomical community, which is what you would expect, which is what you would hope for. And so, I'm going to be giving you a lot of updates, I'm sure, as we go. So has dark matter been found? Not exactly. A signature that might be associated with dark matter has been found, but, obviously more time will tell. I've got a story about this from Mark Thompson on Universe Today. At the very beginning of the universe, we had primordial hydrogen and helium, and that's what went in to form the very first stars of the universe, not the metal-polluted stars like our sun is much later on in the universe. The problem is that those first stars are obscured by the cold molecular gas that was in the universe at the time. This is why astronomers call this the dark ages of the universe. And there might be a way that we can map out the dark ages of the universe using very special radio telescopes built on the far side of the moon, but we're still a few decades away from that being a possible observation. But now astronomers think they've found a galaxy, which is an analog of one that you would have seen at the very beginning of the universe. It seems to have no metal, lots of stars, but no metal. Now, of course, when astronomers talk about metal, they're talking about anything that has more protons than helium. So, Carbon is a metal. Oxygen is a metal. They're seeing this galaxy at 11 billion years ago, which is a few billion years after the Big Bang. And so long after, galaxies like this should have formed multiple generations of stars and polluted themselves with all of that metal. And yet this one looks pristine. And the reason seems to be that it was isolated. It wasn't part of all of the galaxies that were all forming together and interacting with each other and causing tidal forces, that this was just a giant blob of hydrogen and helium that was far away from the rest of the galaxies and formed in isolation and formed very late and very slowly. And so the galaxy itself, even though we're seeing it 11 billion years ago, only looks like it's about 2 million years old and all the stars in it. And so when astronomers calculate the metallicity of this galaxy, it's the upper limit is 0.7% of the metallicity of the sun. And that is just extremely low. So this isn't filled with population 3 stars, the first stars at the beginning of the universe, but this is maybe what those stars could look like and the distribution of them in this galaxy. We've got a story about this from Andy Thomaswick on Universe Today. Over a year ago, I interviewed Dr. David Kipping from Cool Worlds. And of course, he is obsessed with exomoons. And he revealed to me in this interview that he had gotten time on James Webb Space Telescope, and like a lot of time, to search for an exomoon at Kepler 167e. And then they took their data, and then they had a year to crunch their data. And did they find a moon orbiting around a planet at 167e? Well, unfortunately, the results are inconclusive. And that's the worst kind of conclusive. They took the data, ran a bunch of simulations, and in some of their data models, they got what looks like a moon in the data. And then in others, it was more that it was a sunspot, or maybe lining up the planet and the moon and the sunspot. And so they didn't feel like it was conclusive enough to say, yes, we did indeed find a planet. Now, this is the short version of this. David has done a whole video where he talks about what it was like to go through this process, and it was quite revealing. And I think, what was really exciting about it was how you can see astronomers and scientists, when they get to this sort of zone where it's not enough data and they have to be honest with the data and say, that was a null result or that was inconclusive. And I think, kudos to David and his team for doing that. And hopefully they're going to get more time on Webb to come back, take more observations, and maybe this time they'll be able to find an exomoon. We've got a story that goes into more detail from Andy Thomaswick. But speaking of exomoons, another team claims that they've found evidence of an exomoon. And this time it's around the planet HD 206893b, which is about 133 light years away. Now, this planet is very far away from its star. It takes about 25 years to orbit once around, and it's very big. It's about 1.25 times the size of Jupiter, about 28 times the mass of Jupiter. And that's the perfect kind of planet that you might find an exomoon. And so what makes this different, while David Kipping and his team were using the transit method, they were looking at the light as it was passing from the star through the planet, through potentially the atmosphere of the planet, looking at how the light changed as the planet was passing in front. This team was using the technique of astrometry. And, I've gone on about astrometry as one of my favorite techniques for finding all kinds of stuff. But in this case, they use it to find planets. Now, this wasn't Gaia, although Gaia is an astrometry mission. This was using the Very Large Telescope and an instrument on board that's called gravity. And so the astronomers measured the wobbles of the star as the planet was going around the star. And then they claim that they measured the presence of the moon going around the planet, going around the star. And according to their data, they say that they see a secondary wobble where the object is orbiting every 0.76 years and has about 40% the mass of Jupiter. So a moon that's about 40% the mass of Jupiter takes almost a year to orbit around a planet that is much bigger than Jupiter and much heavier than Jupiter. This would be amazing if true. But yet it's going to require a lot of confirmation, and I'm sure there's going to be a lot of pushback, and I'm sure David is very well aware of this announcement. So if you want to read more about that, we've got a story from Lawrence Tugnetti. Now, we have been tracking the ongoing reusable launch plans of SpaceX and New Glenn. Now, on the Falcon 9 side, SpaceX has been launching reusable rockets for a long time now, and they're very successful. They've seen rockets that have launched and landed more than a dozen times. And China is trying to catch up quickly into this space, pardon the pun. They've actually got a bunch of companies that are working on this, as well as some efforts from the government itself. And so the company that is the farthest along, a company called Landspace, just completed a test launch of their new rocket, which is called the Juche 3. And Juche 3 is made of stainless steel, has 9 engines that are powered by methane and liquid oxygen. We've seen some tests where they've gone up and come back down and landed safely, but this was like a full, let's launch a satellite into orbit. And so this week they launched from China and they were able to reach orbit. The booster and the upper stage separated successfully. And then the booster continued on several hundred kilometers downrange and tried to make its descent burn. And it did a very long burn, about 46 seconds, which sounds like a very conservative attempt to try and land this rocket. And then it seemed to have some kind of anomaly just before it touched down, and then it splatted onto the ground and didn't quite hit the target. You see images of the target and sort of where it struck the ground. So they were able to make it to orbit, but they weren't able to successfully reclaim the booster. And, this isn't a direct analogy of the Falcon 9, because the Falcon 9 uses kerosene. And so this is using the same kind of fuel as Starship, but it's a smaller rocket. Same kind of fuel that New Glenn uses, but it's a smaller rocket. So you can see that China is moving. And in fact, I mentioned that the government is getting in on the action. So they're going to be doing a test in later December with the Long March 12A, which is going to be another version of a reusable first stage using methalox. And they're going to try to recover that first stage. And I think we're going to see a lot of companies out of China going down this pathway. Nobody is catching up to the mega rockets, Starship, New Glenn, but I'm sure that'll be next as well. Every week, we do a vote on our channel where you tell us what you thought was the best space news story of the week. And the winner last week was that Russia has lost their launch pad for sending humans to space. So thank you, everybody who voted last week. We're going to put the new vote into the post tab here on our channel. Go check out the post tab, vote a bunch of times, subscribe to the channel, click on the notifications bell, and that will maximize your chance of seeing these in the future. One of the big unsolved mysteries in cosmology is that why is there more matter in the universe than antimatter? It's believed that back at the beginning of the universe, there were equal amounts of matter and antimatter, and then they collided and were left with, for some reason, a little bit more matter. And that's why the universe is filled with matter and not clouds of antimatter still around that collide and annihilate and release tons of gamma radiation. Where did all the antimatter go? All right, so we're going to go through some particle physics now to try and sort of get to a possible answer for this. So there are a bunch of conserved qualities in particle physics. So charge is one of them. So you imagine you have 2 neutrons, you smash them into each other close to the speed of light, they're going to throw out a bunch of particles. If you chase down each one of those particles and you add up the charges on all those particles, they should average out to 0, because neutrons have 0 charge, charge is conserved, you need to have the charges be the same. And that's one. And there's another, which is parity. And there's another one, which is time. When you put those together, you get CPT. Symmetry. But there are a couple of anomalies to this sort of expectation of parity. So there's CP violation, where the weak force, where you don't need to have symmetry in charge and parity. But there's nothing that allows for parity and time asymmetry. And that's what you would have needed to be able to get different amounts of matter and antimatter. In a new paper, researchers looked at the kinds of dark matter particles that are interesting candidates for dark matter. So one is the axion, another one is known as the sterile neutrino. And they didn't focus just on the particles themselves, but on their symmetries. And they found that they can form soliton knots within energy fields, and that this will trigger an asymmetrical decay with more matter particles than antimatter. And so if there were these knots there in the early universe, and these things match what could be created through axions and sterile neutrinos, then this could explain the matter-antimatter parity. And what's kind of exciting about this is that these knots would have been there at the beginning of the universe, and then they would have sort of expanded over time, and they could be detectable through gravitational wave observatories. Not the current ones, but maybe really powerful ones in the future. We've got a really interesting story about this from Dr. Brian Koberlein on Universe Today. So if you remember back in 2018, scientists announced they'd found liquid water underneath the surface of Mars. And this was thought to be a briny liquid water under the south pole of the planet. And this observation was made using the European Space Agency's Mars Express mission, which has a ground-penetrating radar system that allowed it to look beneath the surface and detected the reflection of what looked to be liquid water under the surface of Mars. This is a big announcement, and so you want confirmation. And there was another instrument in orbit around Mars that could try to take a crack at it, and that was NASA's Mars Reconnaissance Orbiter. It's also equipped with a ground-penetrating radar system. But the problem is that it was configured in a way that made it really tough for it to be able to make that observation. And so last year, NASA did a maneuver with Mars Reconnaissance Orbiter where they sort of flipped it over on its side because the bulk of the spacecraft was interfering with the radar observations it was trying to make at the south pole of Mars. And so this was considered a kind of a risky maneuver, and so they held off. But now it's like such an old spacecraft, we're well into overtime, so they gave it a shot. And we reported on this maneuver, and they were able to make much better subsurface detections with its subsurface radar system. And so they scanned the same area that Mars Express had scanned, and unfortunately, they didn't pick up the presence of liquid water under the surface. And so now the researchers are suggesting that maybe it wasn't water at all, it was just flat rocks that were causing this reflection, which is too bad because it would have been cool if there was liquid water on Mars. Got a story about this from Andy Thomaswick. Happy 25th anniversary to the Gemini South Telescope. And this is, of course, the sister telescope to the Gemini North. These are both monster telescopes, 8.1 meters, and have given some of the greatest images that we've seen. In fact, it gave us the nicest images of 3i Atlas that we've seen so far. And so to celebrate the 25th anniversary, they released this beautiful picture of the Butterfly Nebula, which is a planetary nebula. It's located about 3,000 light years away. And, you know, this is visible in small telescopes. People can take pictures of it. It's located in the constellation of Scorpius. And what's interesting about this object is that there is a white dwarf that's at the center. Now, a planetary nebula, this is like when a star like the sun reaches the end of its life and it puffs off its outer layers and you're left with the core. And I really love this idea, right? Because essentially the star has shed all of the outer layers, the radiative zone, the convective zone, and you're left with just the core. So this star is very hot, one of the hottest white dwarfs ever seen, 250,000 Celsius. And now it is just cooling down. Eventually, over trillions of years, will reach the background temperature of the universe. And each planetary nebula is different because of the interactions with the star and its environment. And so in the Butterfly Nebula, you have these huge double lobes of material that are blasting out from it. It's a great object, great telescope. And we've got a story about this from Evan Goff. I hope you're enjoying all the space news that I'm hurling at you this week. Now, you're watching this over on YouTube, and, you know, there are some downsides with YouTube. They want to put a lot of ads into it. They want to kind of separate you as the viewer from us as the creator, and then try and jam a lot of AI wherever they can. And so we actually think that over on Patreon, it's a much better viewing experience. There are no ads. Every time we post a new video, you'll get an email that tells you, and it's completely free. You don't have to pay us any money to watch our stuff over on Patreon. So we've got a version of this exact video, but with one more story. And that bonus story is how the Gaia telescope, my favorite, helped track down a supernova that hit the Earth 10 million years ago. So I'm going to put a link in the show notes. You can go watch that episode, which is the same as this episode, but with one more story. And then follow us on Patreon, and then you'll get announcements of every new time we post any of our content and not be beholden to the YouTube algorithm. But if you want even more space news, we're covering like 30 to 40 different stories over on Universe Today every week with a huge team of dedicated science writers. And it's way too many for us to cover here in Space Bites. But I write a weekly email newsletter where I pull together all of the stories that we're covering over on Universe Today. And then I write the entire thing myself by hand. No AI. I have to keep saying that everything is no AI. Anyway, it's completely free. I write every word. There's no ads. You can just subscribe, unsubscribe anytime you like, and you can get that from universetoday.com/newsletter. All right, those are all the news stories that we had this week. I'm going to talk a bit about sort of what happens next with Universe Today as I return back to Canada. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Carabon, Chuck Hawkins, Commander Bailock, Cy Nielsen, Dark Finga, Dave Veribach, David Giltonen, David Matz, Evan Pro, Greg Feely, James Cook, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Spitz, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Roebuck, Brinkaidu, Richard Williams, Sean Sojan, Stephen Finley Munley, Team 49, Telescopes Canada, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So the time I'm recording this, we're wrapping up our stay in Krabi, which is in southern Thailand, and then we're going to be moving to one final location that's going to put us near a national park in Thailand. And the hope is that we're going to be able to see elephants in the wild, but other wildlife and lots of bugs. I'll be back in Canada in about a week from now. And so this is going to be the last episode that I'll be recording on the road. And so next time you see me, I will be less disheveled and back in my regular studio. I'll also be starting up the live streams the week after that, as well as all of the other stuff that we do. I've got a lot of interesting interviews planned as well. So expect a deluge of content. So thank you everybody for sort of supporting us as we are on the road for this last month. Had a great time. I'm ready to get home though. And I am definitely looking forward to lots more interesting space news. All right. We'll see you next week.